Okay, here's a predict the starting material problem where the target is an alkene that's optically active, and this alkene has a possibility of diastereomers. So when you have an alkene with a possibility of diastereomers, you definitely want to be thinking of the E2 reaction, especially the anticoplanar rule. And our conditions are tosyl chloride and triethylamine followed by potassium tert-butoxide. What tosyl chloride specializes in is it changes the OH into an OTS group without affecting the stereochemistry at all. And tert-butoxide is good for during an elimination reaction on the less hindered side. So the first thing to do is figure out where the alpha carbon is and where the beta carbon is. And so what we'll do first of all is just routinely just put in a tosyl chloride, well, a tosylate group I should say, on either one, and then evaluate which one would have the anticoplanar rule apply. And so when we do this reaction, in order for the anticoplanar rule to apply, the alpha carbon and beta carbon must both be chiral centers. In this case, the alpha carbon on the top one is a chiral center, the beta carbon is not. As a result, you get a mixture of diastereomers. Here, both the alpha carbon and beta carbon are chiral centers, so that suggests that that is indeed the right structure. So, therefore, we're looking for an OH attached to the same carbon as the deuterium to give the best product. And so that suggests A and C and eliminates B and D. Next thing to do is check on the stereochemistry. Now we know this product is optically active. This chiral center right here is set. That chiral center has to be the same chiral center as the starting material. So this chiral center is an R chiral center. So we double check. That is indeed an R chiral center, and that's an R chiral center. Okay, so that doesn't rule out A or C. Next, it's a matter of drawing in stereochemistry. And so we're going to add the OTS here, and the hydrogen is going to go on there. Now, by the anticoplanar rule, if the leaving group is a wedge, that means the hydrogen must be a dash. Therefore, that methyl group is a wedge. That's one possibility. The other possibility is the leaving group being a dash. In that case, the hydrogen is a wedge, meaning the methyl group then is a dash. That's the other possibility. And so these two, either one of these structures, upon elimination with tert-butoxide, can give the alkene. And so therefore the alcohol would have the same stereochemistry because tosyl chloride doesn't change the stereochemistry. So we're looking at for one of these two molecules. And again, we can compare R and S on these. This is an R chiral center. and this is an R chiral center. So we're either looking for an RR, or this is an S chiral center, this is an S chiral center, or an SS. So this molecule here, 1, 2, 3, that's an R chiral center. 1, 2, 3, that's also an R chiral center. So that's a possibility. Here, 1, 2, 3, that's an S chiral center. 1, 2, 3. That's an S chiral center. So that's a possibility as well. And something did not work. Went about this too fast. Here we had two possibilities. Let's double check. Here this is a dash, here that's a dash here. So something was wrong when I was declaring R and S on those. Let's take a look at this a little bit slower, just to make sure. 1, 2, 3. Hand goes up. That's S. 1, 2, 3. Hand goes up. That's also S. Sorry, that should be R, S. That doesn't match. This one's SS. That one does match. So easy to make a mistake. But that is the product. Now, a way of double checking just to be sure is you can plug the material into this equation to see if it actually works out. So that's this molecule here. OH, D, tosyl chloride triethylamine, makes this an OTS, and doesn't affect the stereochemistry. Potassium terbutoxide does an E2 elimination. That is an alpha carbon is primary, but since we're using a bulky base, we can still eliminate it. Now to figure out the stereochemistry of this, the hydrogen and the OTS group must be anticoplanar to each other. So right now, that hydrogen is a wedge. And that tosyl group is a dash. My pin's not working. Okay, pin's not working. That's unfortunate. Visual. Okay. The hydrogen's a wedge. That means we have to make that tosyl group a dash. If we rotate this 180 degrees, that OTS becomes this. Actually, we want to rotate 180 degrees so that OTS becomes a dash to the top. And now the hydrogen and the OTS group are opposite each other. So when you do the elimination, you draw the lines as the same, add in the double bond, and add in that, and we get the deuterium and the methyl group cis to each other, and in the product, the deuterium and the methyl group are cis to each other. So it checks out.